Well, thanks for coming, and I'll try not to keep you too long, but I do have some things that I did want to show to you today, talking about some things that we've done with the latest Intel processors to make it easier to debug and help you find things during your boot time. I'll be talking basically about the Intel processor trace buffer features. Over time, these features have gotten more and more rich. If you go back to like the early Pentium days, you could find out things if you were on the front side bus, but you couldn't really do these types of things with just software. So in the last few years, they've added ways that the software can go in, the firmware that's running, or the software can go in and find out what's been happening on the bus. I have a couple of examples of things that we've done to use these features. The driver profiling, which can show you some interesting information, and then some work on code coverage, which is always useful. So what we're talking about here, usually you have, if you want to go back to the old days of being able to capture information to do debug, a lot of times you had to have physical access to the board. And usually that physical access came in the form of some sort of large connector with a lot of wires on it, somewhere between 30, 60 to a couple of hundred wires. And so you would end up with this massive connection that you'd want to make to the board to be able to do any sort of reasonable debug. The good thing about it is it had almost no impact to the software that was running. Right? Occasionally it would have a little bit. For the most part, you could pretty much guarantee that things would work on a board without the debugger and on a board with the debugger. Then we started creating software debuggers for PCs. This had the advantage that it doesn't really need physical access. You could do it over a network cable, you can do it over serial cables, and anything in between. The problem with it is it does have impact to the software execution. So if you're sitting there and you're tracing through your boot flow, you're going to slow down the system a lot to be able to watch what's going on. So there's this complexity of sharing the processor with the code that's being debugged and the code that is doing the debugging. So to define some terms here, you have the host machine, which is the machine the programmer is using to do the debug. And then you have the target machine, which is the platform that's actually doing the execution and going through the process. Now you can, like, as I said, you can hook up to any number of different cables. These are some of the ones that we support with our software debugger we call H2O DDT. The target platform's running the BIOS in this case, or the UEFI firmware, and is providing the interface to the system. The user interface is running on the host machine. So that's the one that the programmer is sitting there looking at. Up until this time, we had to, every time we wanted to do any sort of trace, the debugger would have to set an instruction flag in the processor on the target machine and tell it to do a break on some condition. Sometimes you would do a break on the next instruction, and you would collect the information, the break would happen, then you would collect some information on the target machine, and you'd send it back to the host. And in some cases, you'd save it in a local buffer. And then you'd go through the process, and you'd look at various debug control information, and you'd say, okay, did the user want me to break at this point, or do I need to just go on? Is he have some condition set up so that they want me to break on a AL register equals some value, or a particular write to an IO location. And if none of your conditions happen, you just go ahead and restart and go to the next instruction. So you can imagine that you've got hundreds and hundreds of instructions that the debugger is running on the target processor while you're going through and debugging each instruction in the code that you're trying to debug. So with branch tracing, what we've got is we've got this buffer. It can be anywhere from like 4K to several 24K to like 4 megabytes long. And in that buffer are the trace records that are happening. And these are very similar to the trace records that the American Ariums or the ITPs were using in the past. And they were snooping it off of the front side bus, whereas we're actually just the processors collecting it and putting it into some memory for us. So now what happens is the debugger sets up the conditions in the processors, and then whenever the break happens, all the debugger has to do is go back and go through this trace buffer to figure out where the processor has come from. So you can, on any break, you can find, if the buffer's deep enough, you can go all the way back to the previous break, and you can see all of the code that's executed. So this allows a target processor to basically run without any impact. Now, obviously, you're going to be saving these branch messages into memory somewhere, so that's going to slow down the processor some. In our testing, though, we've noticed that the slowdown is anywhere from almost nothing, imperceptible, or it's can be as much as like twice. But that's still a whole lot faster than the old methods of doing everything with a software debugger. So the branch record, just to give you an example, and so that I'd have some technical slides up here, the branch records have a limited amount of information. And basically it says, here's the branch from, here's where I'm going to, and whether or not this branch was actually taken or not. So there's a lot of other fields that are available, but these are the basic ones that we look at. The cool thing about this is it allows us to solve some problems that we've never really been able to solve in a software debugger. You would have to have an ITP or some other logic analyzer to grab hold of the bus to actually see some of these things. We can actually unravel call trees all the way back. We can highlight areas that were called by an OS during post, or as you're bringing the OS up, actually. We can find long hardware I/O loops, and we can point those out to the programmer so that if you have a really slow post process, it allows you to go through and figure that out and find out where you're spending all your time. If the system were to crash, we can spot that sometimes, and then we can go out, we can stop the processor and actually break and cause things to happen and allow you to debug and figure out why the system has crashed. One of the things that I'm going to show, or the two things I'm going to show today, is going through and looking at the code coverage. So if you run a test and the code executes the test, and then you can go back and you can see, well, how much of the actual routines were executed. And then I'll show profiling, some performance profiling with drivers. As I'm sitting here looking at the guys from Phoenix, I want to do want to point out that these features, I'm sure these features are available in other debuggers from Phoenix and from AMI. Okay, so profiling drivers. Basically, all you have to do is the debug driver that's running in the BIOS. You have to update that to support something like this code, and then you rebuild your BIOS. You have to turn off the optimization because you don't want to optimize too much of the code, or it makes it extremely difficult for us to figure out what's going on. And then you generate the debug information. All of this information gets put into the PDF files, no, not PDF, PBD files, and yeah, it's a PDF file. No, it's one of the output files from the compiler, and you can get this information. We end up knowing where the C code line numbers correspond to the assembly language instructions that are being executed. Then in the debugger, you just turn on a few flags. You have to tell us some information, and then you can enable and disable the profiling. Usually the debugger is going to have some sort of profiling menu, and you can just enable it and disable it. Then you let the system run, and it runs to whatever condition you want it to run to. And then the way we do this is we have a post-processing sequence that runs through, does all the performance analysis for you, and gives you some menus that allow you to select exactly what you want to see and generate some reports. And then, so this goes back to the previous point of we allow 24K to 4 megabytes in the PEI mode. And then when you get into Dixie mode, we have a different buffer that we set aside so that you can have this huge, massive number of trace records. So this is an example of the profiling execution. You can see over on the left-hand side is the path that you went through during post, or while this driver was executing. You're going through this path, and then at this point, here's the code that was executing. Now, in this case, all of the code, it was a straight inline code with a for loop and some other things going on, but all of this code actually ended up being executed. So we actually highlight this code in green so that it makes it stand out from any code. Well, for example, this instruction here, for some reason, did not get executed. Seems strange. That's probably where the bug is. So code coverage, over the last 10 years or so, I've gotten very interested in test because the BIOSes have gotten so complex that it's gotten extremely hard to know if the code that you have, like saying from my kernel team, right, is the code that they're generating well tested? Because if it's not, then I can't really prove to a customer that the code is correct. So one of the things that I've spent a lot of time on at Insyde is in trying to improve our test coverage. And one of the failures that I had for the longest time was I had no way of knowing how much of the code was actually tested. So one of the reasons that we created this code was to help with our internal validation. Because we realized that if the code wasn't being tested during the QA testing, then the code was either unnecessary, right? There were exceptions happening that never got tested, or never could get executed. So we needed to remove that code and make it smaller so that it would load faster, or it was not being tested, in which case there was a high likelihood that something would happen out in the field where an exception would happen and it would go out into the weeds someplace, right? There were all sorts of cases. Even today, if you go look in Tiano Core, there are still some places where the code just hangs in a production system because it's an error condition that should never happen. Well, if there's an error condition that never happens, we don't need code to handle the error. If it's ever going to happen, we need to make sure that there's code there to handle it. Okay, so these are some of the reasons that we feel the need for code coverage testing. So this is an example. It's a fairly contrived example of some code that's running during power on and making sure that the code goes all the way through and that everything gets executed when we're doing a test. So you can see that in these two modules seem to be fairly highly well tested. They go through 280 times during post. You can see that these are fairly well tested. Then all of a sudden you run across a couple of these 6 different modules here that no one ever calls during the test. And then you can see over here on this side, on the right-hand side, you can see we go through here, we do some testing, we can't really figure out on some of these cases if the code ran or not. So that's something that you need to sit down, and a programmer needs to make sure that they understand what's happening. And then this routine right here, core search map entry, some kind of map entry, never gets executed at all in this test. So either you need to go create some other test to test that routine, or you need to get rid of that code. That is an example of some things that you can do with a simple debugger, a simple change to a debugger, and with the latest Intel processors. Similar types of things are available in our debugger for AMD processors. This example just happens to be something that was worked on just for Intel processors. Okay? Call your debugger supplier and ask them if they support these kind of features, and drive them so that they do. Profile your drivers, right? Go out. If you write a third-party driver for a BIOS, for a piece of hardware, you can do the same type of profiling. You can get an idea whether or not you test all the conditions in your code. And then when you're doing your test cases, you can check and see how much of your code actually gets executed. So these are good things that can happen that you should do. Thanks. If you want more information, my presentation will be posted, and this is some information on Intel processors. It gets pretty hairy with looking at all the different processors and what type of support is available in each one. There's like 10 different generations of processors documented in this manual. So good luck trying to figure it out without a flow chart or something. And then we have our developer tools. We discuss our developer tools on our website. Thanks. Oh, anybody got questions? I see a hand, Mr. Simpson. At this point, the question was there any new hardware support that was required to support this, to support the trace buffer? And the answer was yes, there was new hardware required in the processor, because older processors did not have any sort of support for letting you know when the code was actually going to execute, what was happening, what the instruction, so if you had a front side bus, if you had access to the front side bus, you collect the fact that you did all these data reads, right? But you didn't necessarily know, just because you read a chunk of code in, you didn't know that it was going to be executed, right? Because you'd just be doing speculative cache fills, right? So that was the reason for the trace messages in the first place. But for this, the software debuggers never really, without being able to do something like an instruction by instruction stop to go out and collect the information, you didn't really know, the software debugger didn't really know what code was executing, right? If you set up a breakpoint at a particular location, you just assume that you got there reasonably, right? But in a lot of cases, you didn't get there reasonably, right? You got there because some system crashed or some pointer got off, and you're just randomly writing through memory or something, right? And all of a sudden you hit that particular location. So there is in this generation of Intel processor, there is a large buffer where the processor, every time the processor does works on a branch instruction stores information about that branch instruction to let you know whether or not it was taken or it was not taken and the conditions around that. Are there any plans to support NVDIMMs? Knowing what I know about NVDIMMs, which admittedly is not, I'm not the expert in my team on NVDIMMs, there should be no reason why we couldn't already support you. Right? We already have the ability to read your configuration data out of your SPD devices, so we can display that. We know what the format of that information is, so that's fully displayable. We understand the memory registers in the processor or in the North Bridge, and so we can display that type of information. What we have not done is figured out or is provided a way to look at what your backing store is that's actually your NV part. So that's a good question. Probably a good idea for a debugger. I'll write it down. And we'll work with you on it. So the question so far is, does this feature work when you have optimizing compilers? So like if your compiler got rid of any sort of dead code that it found. Typically, when you're doing UEFI code, you don't really want the compiler getting rid of dead code, because sometimes its algorithm for detecting dead code is not quite as good as it should be. But, and we definitely suggest turning off optimization when you're running this, just because it makes it a lot more difficult for us to figure out, for us to do the unwinding and making the connection between the assembly or the machine code and the C code that we're trying to display to the programmer. Yeah, any sort of optimizations cause us problems in the debugger. But obviously sometimes that's what you're trying to debug.